Hello, everybody. We will be live at 5:30.
Good to know. Okay, we're going to be starting here in just a few moments. Well, I have 5:30 Central Daylight Time. Hi everyone, my name is Mike Randall. I'll be your presenter for the physics experience. Also say hello to my lovely wife. She's the extra set of hands I have here today. Her name's Tara. Um, we're presenting the physics experience as part of this year's UW-Madison Science Expeditions event. Um, Welcome to all of you, and even welcome to have a friend of mine who's promoting this in India through a group called Business Value India. And so, if anybody in India is up at 4 a.m., hello. Tara says hi too. Anyway, today we're going to be talking about physics. We're going to talk about what physics is, what it has to do with all of you. Mostly, we're here to have fun today. Hope you're okay with that. And one thing I want you to really get, if you don't take anything else away from the show, get one thing. You are a physicist. You are a physicist. You've been using physics your entire lives. You're really good at it. I'm going to give you a couple demonstrations of that during the show today. I guess before we talk about physics, we should actually know what physics is. So there's a lot of different definitions for physics. Here's my definition. And I'm going to have a robotic cameraman here, so I'm going to zoom in a little bit. All right, physics. Physics is the study of stuff. Stuff, like the wall behind me, the floor I'm standing on, my head, me, stuff. But scientists have a different word for everything. Scientists don't call stuff stuff. Scientists call stuff matter. So physics is the study of matter or stuff. And we're not done. Physics is also the study of how you move stuff around. Think about it. What gives you the ability to move stuff around? It's a one-word answer, starts with the letter E. Oh, and before I forget, if you have any questions during the show, type them in the chat. We will allow some time at the end of the show, and I'll get to as many of those questions as I can, okay? Anyway, the word that I was looking for, by the way, is energy. Energy. Energy is the ability to do work. It's the ability to do anything. So physics is a study of matter and energy and how those two things play with each other, how they interact. Now that covers a lot of things. It covers movement, like throwing a ball. It also covers sound you can hear, light you can see, heat you can feel, electricity, magnetism, and a whole bunch of other stuff lumped together in a category called modern physics. So I'm going to give you a really cool demonstration of that later in the show using lasers. Now, we can't really talk about physics without talking about one of my favorite dead guys. Yeah, this guy was widely regarded as the father of physics. Really smart guy, Sir Isaac Newton. Maybe you've heard of him. Really sharp guy. Came up with a lot of great ideas about how the world works, including 3 ideas on how things move. His famous Newton's 3 laws of motion. So I'm going to give you my version of Newton's laws. Okay, for Newton's first law. Newton's first law says that stuff wants to keep doing what it's already doing. Stuff wants to keep doing what it's already doing. So this basketball is made of stuff. If it's sitting still, it wants to keep sitting still. If it's moving, it wants to move in a perfectly straight line at exactly the same speed forever, or until something outside of it pushes or pulls on it. That was pretty easy. Newton's first law. Done. For Newton's second law, it's a little more complicated, but it's not that hard. Newton's second law says that force, mass, and acceleration all go together. Well, what's all that? Well, force is simply a push or a pull. Okay, that's easy. Mass is how much stuff is there in something. So this ball is made out of matter, but if I measured how much stuff is in this ball, how much matter is here, that measure would be called its mass. It's just how much stuff is there. And acceleration is pretty easy too. Acceleration is simply a change in speed or direction. Okay? Those 3 things go together. Force, mass, and acceleration all go together. And you already know this. You do. How do I know that? Because I've done hundreds and hundreds of these shows for people all around the country and all over the place. And every time when I would do it live, I would have someone from the audience come and help me, and they always got it right. Here's what I'm talking about. So if I asked any one of you to come here, like maybe you could magically teleport here, and I asked you to throw this ball to me, you wouldn't have any problem doing that, right? You'd say, oh, okay, here's the ball. It's, I get about how heavy it is. I'm going to push it this hard to make sure it's going fast enough to fly through the air and make it to me. That's a no-brainer. You're so good at this, you don't even have to think about it. We'll talk more about that later. All right, that's great. What if I changed it up on you? What if I gave you this ball? This is a medicine ball. A lot more mass. You know what? You'd get this right too. Because you'd go, more mass means I have to apply a bigger force. to get the ball accelerating fast enough to get over to me. You don't even have to think about it. You are a physicist. You know how it works, and you would demonstrate a perfectly demonstrate Newton's second law. All right, Newton's first law, Newton's second law. For Newton's third law, I'm going to have my robotic cameraman go a little bit over here. Now, something I didn't tell you at the beginning of the show. I used to be a rocket scientist. I'm not kidding about that. I used to work on the space shuttle main engines and other rocket engines. So I happen to know that Newton's third law is often referred to as the law of rockets. And here's why. In a rocket engine, I know this isn't a rocket engine, it's a leaf blower, but the idea is still the same. So in a rocket engine, or leaf blower, a lot of gas goes this way, and the rocket, or leaf blower, goes this way. Sir Isaac Newton would have said for every action, there is an equal and opposite reaction. Maybe you've heard that. Or another way I like to put it is like if you push against something, it pushes back. Okay, that's pretty easy however you cut it. So let's try it out. Now what you can't see is right down here, there's a turntable here on the floor. I'm going to stand on this. Oh, I hate this part of the show. There we go. Ugh. Okay, here we go. What do you think is going to happen when I turn this leaf blower on? Huh? Just kidding. I actually love that part of the show. Yeah, but you saw what happened, right? The air went this way, and I went that way. Newton's third law. So now you know all three of Newton's laws. I challenge you to look for how you're already using all three of those laws out in your life. I guarantee you, you're using them all over the place, and you're really good at it. Okay, let's talk about energy. I mentioned that at the beginning of the show. So energy is the ability to do work. It's the ability to do anything. There are many different forms of energy out there, but they all have two weird things in common. Ready for this? Weird fact number one, you can't make energy. Can't do it. Don't feel bad, I can't do it either. Nobody can. You cannot make energy. Weird fact number two, you can't get rid of it either. What? You can't make it, you can't get rid of it? You can turn it from one form into another, and you're all really good at this. I'm going to prove it to all of you right now. So everyone who's watching, put your hands up in front of you like this. Put your hands together like this, and start rubbing your hands together. Keep rubbing those hands together. And stop. What did you just notice? Well, you probably noticed your hands got warm, right? Heat. Heat is a form of energy. So you just made heat energy, right? No, no, no. You can't make energy. You had to turn some other kind of energy into heat energy. What kind of energy did you turn into heat energy? Well, I'm giving you a clue. Your hands are moving, right? Movement is another form of energy. Scientists even have a word for that. They call it kinetic energy. Kinetic energy, energy movement. So somehow you turned movement energy or kinetic energy into heat energy. Well, that actually happened through a process called friction. Friction is a force that when things are touching, it makes them stick together. And when things are touching and moving, friction is the force that turns the movement energy into heat energy. We'll talk more about heat energy later. Okay, we're not done. Where did the movement energy come from? It's a little harder to think about this. Well, do you eat food? Well, of course you do. Why do you eat food? You eat food because there's energy stored in the food. Scientists have a word for that. They call it potential energy. Potential energy means stored energy. You eat food that goes into your body, and it's stored up in your body until you need to move. Then your body sends that food energy to your muscles. Your muscles turn that into movement energy. Friction in your skin turns that to heat energy just that quick. You go from one kind of energy to another to another. This happens all the time. You do this all the time. You are such experts at this, you don't even realize you're doing it. Now, seriously, think about that. Have you ever watched someone playing basketball? Like someone who's really good, and they're going down the court and they're going in for a slam dunk. So they take the ball and they just go in and slam dunk. You know what they never do? They never go left foot, right foot, bounce, left foot, right foot, dunk. No, that'd be weird. They don't have to think about it. They're experts. They just do it, and it looks beautiful. You are experts in exactly the same way when it comes to turning energy from one form into another. You are experts at this. You're so good at it, you don't even realize you're doing it. You don't have to think about it. You just do it. You're doing it right now. You're experts at physics. Really. Now, let's go on to the next thing. Let's talk a little bit more about matter and stuff. Something very important for you to know, which will help us to understand things like heat energy later on. All the stuff around us is made of, that we can see, is made of little teeny tiny things that sound like a boy's name. Those little teeny tiny things are called atoms. You've probably heard of them. They're so small that even with our most powerful microscopes, it's really hard to see them. So I'm going to cheat a little bit. I'm going to use marbles to represent atoms. So I'm going to stand a little bit closer so you can kind of see them. So this bottle here is full of marbles. And you can see how tightly they're packed together. So you can kind of hear they're shaking around a little bit, but they're not really moving around in position. This state of matter, this kind of matter or state of matter, would be called a solid, like my head. Here's another one. In this case, the little atoms can slide around past each other. They can take on the shape of a container, but they don't necessarily fill up the whole container. This state of matter would be called a liquid, like the water you drink. And finally, here's another state of matter. In this state of matter, the little atoms are moving around very fast. If you put them in a container, they'll fill up the entire container. This state of matter would be called a gas, like the air you're breathing right now. Solids, liquids, and gases. Did I forget anything? Oh yeah, a very important one. Robot cameraman. It's this one. This is called plasma. If you take any regular matter, solid, liquid, or gas, and you put a lot of energy into it, and I mean a lot. It could be high voltage electricity like we're doing here. It could be extreme amounts of heat energy. It could be high energy lasers. But if you put a lot of energy into matter, you could actually break the matter apart. So what you end up with is those little atoms that are missing pieces called electrons. Electrons are really tiny things, but you can break them off of atoms. So what this plasma is actually a mixture. It's these little free-floating electrons, and it's atoms that are missing electrons. By the way, those are called ions. We'll talk more about those later. Now, let's turn the lights back on. So it's a good thing we don't have a lot of that plasma stuff here on Earth. Did I mention that to make it, you have to dump a lot of energy into it, like high voltage electricity or really high temperatures, hotter than the hottest fire you can imagine? If there was a lot of plasma here on Earth, we would not be having this conversation. In fact, the plasma that is here on Earth in nature is lightning. And we all know how dangerous lightning is. And we'll talk more about lightning and electricity in general a little bit. But it's really dangerous stuff. But if you look up in the night sky, 99% of what you see is plasma, including our sun. Our sun is a giant ball of plasma. It's important stuff. And it's by far the most common ordinary stuff in the universe. I have to say ordinary, because here's the thing. Scientists think there's another kind of matter out there called dark matter, and they actually think that's the most common stuff in the universe. There's one little problem with that. They don't know what it is. They're still trying to figure that out. Hey, maybe one day one of you guys will figure it out. Or maybe they're just wrong and there might be something else. But for now, we're going to stick with the kind of matter that we can play with: solids, liquids, gases, and plasma. Okay, now that we understand a little bit more about atoms, we can actually now have some fun over here with heat energy. Fun fact. Okay, now the heat energy is something that confuses a lot of people, including a lot of adults, and it's really easy. Okay, remember those little atoms I showed you earlier? Okay, what heat energy is the movement energy of those little atoms, or little clumps of atoms that we call molecules. But it's that movement energy of the atoms. That's pretty easy, right? So if something is really hot, it means the atoms in it are jiggling around really fast. If something is cold, it means the atoms are moving very slowly. That's it. That's not hard at all. So I know there's heat energy in the room around me here because if I had a thermometer would tell me it's about, oh, probably about 70 degrees Fahrenheit, about 20 degrees Celsius, whatever temperature scale makes you happy. But if I took a lot of heat energy away from the air in this room, it changes. It actually turns into this stuff. This is called liquid nitrogen. This is crazy, crazy cold. Minus 321 degrees Fahrenheit, minus 196 Celsius. 77 degrees on something called the Kelvin scale. Hey, however you care to measure it, it's super cold, which means two things. Number one, seriously, seriously, this stuff is dangerous. Don't ever play with liquid nitrogen or dry ice, either one, until you go to college and you learn how to handle it correctly and safely. I mean that. Because it's actually dangerous in several ways. So we'll talk about that in a second. Now, I said there was two things. So the first thing is it's dangerous. Be careful with it. Second thing is if you know how to handle it correctly and safely, it's a lot of fun. Let's do a little experiment, shall we? Actually, before I do that, I'm going to show you something that's really amazing. And I'm going to zoom in on this. So, robot cameraman, zoom in. Oops, other way, down. Okay, so here's my liquid nitrogen. See my finger? Don't ever try this until you go to college and learn how to do it right. I'm going to put my finger in the liquid nitrogen. 321 degrees below zero. What do you think is going to happen? Nothing. I'm not going to tell you why, though. Go to college and learn about it. Now, let's do a little experiment. Let me zoom back out a little bit. There we go. What do you think will happen if I put this balloon in the liquid nitrogen? Oh, now wait a minute. Notice something. Notice something. You are a physicist, right? That means you're also scientists. How do I know you're a scientist? Because you just did something that scientists do all the time. When I asked you that question, a thought popped into your head. It was a guess as to what was going to happen next. Scientists have a word for that. They call it a hypothesis. They call it I'm sorry, honey, what do they call it? Hypothesis. My wife's helping me. I need help on that one. Can I just say it's a guess? It's easier to say. It's okay, whatever. Anyway, they come up with a guess and then they set up an experiment and they observe that experiment to see if their guess is correct. That's your job, scientists. Keep your eyes on this balloon. Hang on to your guesses. Let's watch what happens. Okay, the balloon is now touching the liquid nitrogen. Well, it didn't explode, so if that was your guess, your hypothesis was incorrect. See, I can't say it. Doesn't look like much is happening. Wait a minute, something is happening. The balloon is getting smaller. It's shrinking. So it sprung a leak, right? And remember, we're taking heat energy away from the air inside this balloon. Those air atoms in the balloon are now moving very slowly, which means that they're not running into the insides of the balloon as hard. The pressure inside the balloon is dropping. If we take enough heat energy away, the balloon will collapse all the way down into this sad looking thing. Ah, but all the air is still in there. And there's plenty of heat energy out here in the air in the room. So as the heat energy from the room goes back into the balloon, the little air atoms inside the balloon start moving faster and faster. They start running into the walls of the balloon harder and harder. The pressure is going back up. Pretty soon the balloon is right back to normal, like nothing ever happened. Watch out, honey! Watch out! I'm sorry. I'll pick that up later. She's fine. She's fine. Yeah, yeah. She's trying to wave her hand, but she's fine. Anyway, now I mentioned this stuff was dangerous in more than one way. So, by the way, the obvious one is it's really cold. If I, like when I stuck my finger in, if I did that wrong, I would end up going to the hospital with something that hurts really bad called frostbite. I'm told it hurts bad. See, when I was trained, I've never been hurt by it because I know how to handle it correctly and safely. But if you don't handle it right, it could freeze your skin and it hurts really bad. There's another thing that's dangerous about it. If this liquid nitrogen, if I filled this container all the way to the top with liquid nitrogen and I warmed it all back up to room temperature, this one container of liquid nitrogen would make almost 700 containers of gas. Seriously, seriously, never put liquid nitrogen or dry ice into a sealed container. It's a really bad idea. And this is, honey, you're supposed to ask me why this is a bad idea.
Why is it a bad idea?
Oh, thanks for asking, hon. Why is it a bad idea? Well, I'll just show you. So I just put this dipper in here. So I've got a ladle full of liquid nitrogen. I'm going to put it in this nice sturdy steel container. And I've got a big old cork and I have a hammer. This is a really bad idea. Woo! You okay, hon? Yeah, she's fine. Yeah, it exploded. Yeah, she's still with us. I promise I wasn't aiming at you this time.
This time.
Anyway, um, it exploded. It's so yes, all that liquid as it boiled back into a gas, that gas takes up a lot more room, and it pushed and pushed until boom, it blew the cork out. That could be very dangerous. Now, some of you may have noticed, pretty obvious, you might have a question, why is this smoking? Well, guess what? That's not smoke. It's a cloud. It's a real cloud. See, here's the thing that a lot of people don't realize is that, you know about water. We drink water, but water can also be a different state of matter. If you get it cold enough, it turns to ice, right? So ice is a solid. There's liquid water, but there's also water gas, and it's around us all the time. We just can't see it. It's an invisible gas called water vapor. How do I know it's there? Because if you take the air around us and you cool it down enough, the water vapor will turn back into little tiny droplets of liquid water that we can see. That, by the way, when you look up in the sky and you see a cloud, that's what a cloud is. It's millions and millions of little tiny droplets of liquid water. So that's fun. Now, I'm going to zoom back in again, and I'm going to have you guys watch this. I'm going to pour this liquid back into this. This is a special bottle, by the way. I'll talk more about that in a second. It's called a dewar. I'm going to zoom in on this dewar here because I want you to see what the liquid looks like. There we go. There we go. So try to ignore the cloud. Notice what the liquid itself looks like. Ready? Here we go. What's that liquid look like? It looks just like water. Seriously, seriously, do not drink this. You now know enough about liquid nitrogen to know why that would be a seriously bad idea. You know what else is a bad idea? Remember I told you never seal up liquid nitrogen in a bottle? I'm going to seal up the liquid nitrogen in a bottle. Ah! No, this is not dangerous. Remember I told you it's a special bottle? It's designed so that the lid is loose. So if any of this liquid inside the bottle turns into a gas, the gas can just burp out harmlessly. This does not turn into a bomb, but it's a great place to store my liquid nitrogen between shows. Okay. Let's go over here. Robot cameraman, thank you. All right, I'm going to talk a little bit about air. Right now, you are sitting at the bottom of an ocean. How do I know that? I guarantee it's true. Now, I don't know exactly where you are. You could actually be sitting underwater, but that's not what I'm talking about. You're sitting at the bottom of an ocean of air, about 200 miles worth of it over your head. And that air, even though you can't see it, that air is heavy. See the end of my thumb? It's about an inch wide and an inch high. So if you want to do it metrically, it's like about 2.5 centimeters by 2.5 centimeters. Every place I can cover with the end of my thumb, the air is pushing down with the weight of a bowling ball. Okay, that's about 14 pounds. I should look up at what that is in kilograms. Probably about 6 kilograms. It's heavy, right? Every place I can push down with the end of my thumb, it's heavy. So why don't we notice that? It's because the forces are all balanced out. So the bowling ball's worth of air pushing on this side are pushing against the bowling ball's worth of air on that side, and they cancel out and we don't notice it. What would happen if I unbalance the forces? We could do that. These are not magnets. And some people would call these suction cups. Nature does not suck, it pushes. But they do not do anything unless I push them together carefully and I click these little handles. Now, if I try and pull these apart, and I'm not going to fake this, I'm genuinely going to pull on these as hard as I can pull. I can't pull them apart. I can't do it. What's holding them together? I created an imbalance of forces. When I clicked those little handles, it squeezed all the air out from between these two discs. So there's all those bowling balls with the air on the outside pushing them together, but no air on the inside pushing back out to balance it out. It would take about 200 pounds of force, or maybe 80 kilograms of force to pull these apart. I'm not that strong. But I can use science. I can just unclick these handles, boop, boop, and they come right apart very easily. There's another fun thing you could do with air pressure. It was figured out by another one of my favorite dead guys called Bernoulli. And let's zoom out a bit because we're going to need a little bit of room for this one. Bernoulli figured out that when air is going fast over something, it's not pushing down as hard. Well, let's see what happens. I have a little beach ball here and my trusty leaf blower. What do you think will happen if I blow air over the top? Now, I promise you I'm blowing it over the top. I'm not blowing from underneath, so I'm not lifting it from underneath. I'm going to blow air over the top of this ball. Whoops. It happens. No strings. I could even steer it around if I'm very careful. It just hovered in midair as long as the air was blowing. Well, how is that possible? Well, let's take a look at the ball here. So if without the leaf blower, if this is the ball by itself, what are the forces on it? Well, we know that there's air pressure pushing on all sides, and that air pressure cancels out. This side cancels that side. So what is the one force that is still acting on this? The one that just pulled it down, which we all know as gravity. We know about gravity. But when I blow air over the top of it, according to Bernoulli, if I blow air over the top of the ball, it means the air is not pushing down quite as hard, but the air underneath the ball is still pushing just as hard in the other direction. I created a new balance of forces. I balanced the force of gravity pulling down with the force of the air pressure pushing up, and the ball hovered in midair. Many of you have already experienced this. If you've ever flown on an airplane Airplane wings are special. They're curved on top, kind of like this ball is, but they're flat on the bottom. So as the airplane wing slices through the air going over the curved top of the wing has to travel farther than the air going underneath the wing. If the air is traveling further, it has to travel faster. Faster moving air on top means it's not pushing down as hard there, and it's the higher pressure air under the wing that lifts the wing up and the airplane. See, physics is everywhere in our lives. Isn't that cool? Okay. I've got one more to show you here. This is for fun. Um, I used to, as part of my shows, I built a toilet paper shooter. So I attached this special rig to my leaf blower, and I could blow toilet paper all over the room. And it's really cool. Um, except it's a real mess to clean up. And, you know, we need toilet paper for other things, you know. So what I did instead is I found this really fun shiny tape. And I'm going to attach this rig to my leaf blower. Come on, here we go. There we go. Now notice it's clearly aimed over the top of it. So I'm going to blow air over the top of the tape. Let's see what happens. Isn't that fun? The air was moving faster over the top of the tape, not as high air pressure there. The same air pressure as before underneath the tape. It's the air pressure underneath, the higher air pressure that lifted the tape up. Okay. How are we doing for time? Oh, we're in good shape. So let's talk about lasers. I promised you a demonstration at the beginning of the show about modern physics. I was going to use lasers. Modern physics is where Sir Isaac Newton got it wrong. Hey, look, he was a really smart guy, okay? By the way, I don't know if I mentioned this earlier. He lived about 300 years ago, which explains why he's dead. Anyway, really smart guy. So 300 years ago, he's coming up with all these great ideas about how the world works, including a lot of ideas about light. And for 200 years, scientists thought his ideas about light were it. Yeah, about 100 years or so ago, scientists were experimenting with light, and they got results totally different than what Newton predicted, and it freaked them out. So I'm going to use, to demonstrate why they were so freaked out, I'm going to use these laser pointers and this special screen behind me. I'm also going to use a special camera that does better with low light. Tara, will you switch over to the other camera for me, please? Yep, that's the one. There we go. Now, before we get into this too far, these are ordinary laser pointers, okay? I've got a red one, I've got a green one, and I've got a purple one. Laser pointers like these make terrible, terrible toys. Do not play with these. Do not let your friends play with these until you go to college and take laser safety training like I have, okay? Because they're not going to burn you, but they're so intensely bright. If this were to get into your eyes, it could cause you to go permanently blind, okay? Toys aren't supposed to do that. Don't mess around with these. Do learn how to handle them correctly and safely, and then you can have as much fun with them as you want. Now I'm going to use them over on this screen. Like I said, it's a glow-in-the-dark screen. Now I'm sure many of you have played with glow-in-the-dark stuff before. Before that screen will glow, what do you got to do to it to make it glow? Well, you got to shine some light on it, right? Okay, now if Sir Isaac Newton were here, he'd say, hey, that super bright red laser thing of yours, that's so intensely bright, that'll make that screen glow instantly. And you know what? That makes perfect sense. Let's try it out. So I'm going to turn the room lights out here. All right, so here's my red laser. You can see it down on the corner of the screen. Let's try it out. Red laser on my glow screen. Nothing happens. I don't see any glowing. I'm pretty sure you don't see any glowing. Well, that's weird. You know what? Maybe that laser wasn't as bright as I thought it was. Maybe this green laser. This green laser looks pretty bright. Let's try it out. Nothing. I don't see any glowing at all. If Sir Isaac Newton were here, he'd be freaked out right now. Well, the only one I got left is this wimpy purple laser. Shall we try that? Self-portrait, glasses, beard, eyebrows, nose hair. Yeah, I'm not a very good artist. But the question is why? Why will my wimpy purple laser leave this beautiful green glowing trail and my red and my green lasers do nothing? You know what? It took another one of my favorite dead guys to figure this out. One of the smartest guys that's ever lived, and you all know his name. You ever heard of Albert Einstein? Albert figured this out. He said it's not about how bright the light is, it's about how much energy is in the light. Turns out that purple light has more energy in it than green light. Green light has more energy than red light. So what we see as different colors, like when you look at a rainbow, what you see as different colors is really different amounts of energy in the light. And because he figured that out kind of recently, about the past 100 years or so ago, it's called an example of modern physics. By the way, if any of you ever decide to go on to study physics, chances are very good you're going to be studying a lot about modern physics. Why? Well, do you like electronics? Do you like playing with smartphones and video games and things like that? That's all modern physics. And we're just getting started with it. There's this new thing called quantum computing that's going to completely change the world. You might be working on that or something else that I haven't even heard of yet. But it's some really exciting stuff. All right, let's switch back to the other camera, please. Thank you. All right, let's talk a little bit about electricity. So electricity is another thing that a lot of people don't understand, and including a lot of adults, and it's really pretty easy. Remember I told you earlier about a little bit about the plasma and how there's these little teeny tiny things inside of atoms called electrons. Well, that sounds like a dead giveaway. So here's what electricity is. Electricity is the movement energy of those little electrons or other charged particles. We'll talk more about that in a second. It's usually electrons though. So it's the movement energy of them. Okay, that's pretty easy. So how do you get electrons to move around? Well, there's several ways. Here's one. I have a flashlight with a crank on the side of it. So as long as I keep cranking this, I get light out of my flashlight. What's really going on, this by the way is called a generator. So there's a little coil of wire inside of there and a magnet. And as the magnet moves near that coil of wire, the magnetic field pushes on the little electrons in that wire, gets them moving, gives them some of that kinetic energy we talked about earlier. Enough energy to do something useful, like lighting up a light. Most of our electricity comes from gigantic versions of these, okay? Not all of it. Like solar panels, they work in an entirely different way, and that's for a different show. But I encourage you to look up how they work. All right? Here's another way. Another one of my favorite dead guys, his name's Nikola Tesla. And I'm going to zoom in a little bit closer here. Let's go up a little bit. Come on, there we go. Nikola Tesla. He came up with a lot of great ideas about how electricity works, including stuff that we still use to this day. So this is called a Tesla coil. What this does is it takes those little electrons and it shakes them back and forth really hard and really fast. It's called high voltage, high frequency electricity. And it looks like this. I'm going to turn the room lights out again. And here we go. And I have a fluorescent tube here. See that blue spark? That's electricity, high voltage, high frequency electricity jumping over there. Oops, hang on, there we go. Let me turn the room lights back on. Ooh, everything went pink on me. Huh. Well, that's weird. You know, let's turn that camera off and back on again. Oh, I'm going to have to do it. You know, that's the one thing about high voltage, high frequency electricity is sometimes electronics doesn't like it. So I'm going to turn my camera off. Don't worry, I'm still here. But I'm going to turn it back on again. This will take a second for it to kind of recycle itself. Yeah, I haven't figured out how to stop that happening. It does something a little different every show, which makes it very interesting. Can you turn that camera on for me? The start video? No, you hit the start. Yeah, just click on that. There we go. There we are. See, we're back. Interesting thing about electrical energy, it's really easy to turn electrical energy into heat energy. And by the way, one of the places you'll see that used a lot is in your car engine. Now, most cars don't run on electricity, although that's changing more and more all the time. Most cars still run on car fuel. And I actually have a bottle here with a little bit of car fuel in it, a little alcohol in here. You can run cars on it, but it doesn't do anything unless you light it on fire. So here's what we're going to do. I'm going to zoom in on that bottle a little bit. Let's do it this way. Oops, the other way. There we go. Oh, no, not that far. There we go. So what I'm going to do is I'm going to use this Tesla coil to put a little spark of electricity into this bottle. And this bottle's got the alcohol and it's got a little cork on top. The electrical energy turns to heat energy, enough heat energy to light the fuel on fire, makes a little explosion, which pushes on the cork and will shoot the cork out. Very much like the spark plug in your car that lights the car fuel on fire. Okay, here we go. And in 5, 4, 3, 2, 1. Ooh. Oh, sorry, honey. She's fine. I'll take care of that later. I'm just kidding. So let's go up here. All right. So let me do this. There we go. Another way, and actually probably one of the most fun ways that many of you are familiar with, especially if you live in colder climates. Like I'm in Madison, Wisconsin right now, which is in the northern part of the United States. It can be very chilly here, which means the air gets very dry. So in the wintertime, sometimes if you're walking around on carpet and you reach over to touch something metal like a doorknob, zap, a spark will jump off your fingers. Scientists have a name for that. They call it static electricity. What you're really doing is as you're moving your feet on the carpet, you're scraping the little electrons off the carpet and onto your body. Electrons do not like to be crammed together. I mentioned something about charged particles earlier. So electrons are little charged particles. What does that mean? Well, think of it like there's a little force field around them, okay? So if you've ever played with magnets, sometimes magnets like to stick together. But sometimes if you try and push magnets together, they push apart. They repel each other. Electrons do the same thing. If you put a negatively charged electron next to another negatively charged electron, they push apart with tremendous strength for their size. I'm going to give you a demonstration of that in a minute. Now, I have a machine that makes static electricity for me. It's called a Van de Graaff generator. Let's zoom in on that a little bit. Let me show you what it looks like. Now, it's possible I might zap my camera again, so we'll see. Hopefully not. See those sparks? So those sparks look like looks like little baby lightning, doesn't it? And the cracks you hear could be like little baby version of thunder. This is harmless, by the way. I can, ouch, it stings. Don't get me wrong, but it won't send me to the hospital. If you see real lightning or hear real thunder, it's made in a similar way to this. But real lightning is deadly. If you see lightning or hear thunder, get indoors quick, okay? Harmless. Now I'm actually going to use this to actually demonstrate. I mentioned I was a rocket scientist earlier. Let me back out a little bit more. In my rocket science days, I used to work on the space shuttle main engines. Pound for pound, the most powerful machines ever built by man. 500,000 pounds of thrust. They would shake the ground. There's one problem. After about 8 minutes, they're out of gas and they're just dead weight. So what difference does that make? Well, someday some of you might go to Mars. It's true. If you used a regular rocket like the space shuttle type rocket engines to get there, it would take you about 300 days just to get from Earth to Mars. Can you imagine being cooped up in a spaceship for 300 days? Ugh, no thanks. But there's a new type of rocket engine that NASA's already been using called ion propulsion. And I actually have my own ion rocket here with me. Let me demonstrate. Let's zoom in a little closer. Here we go. Ooh, I know. 500,000 pounds of thrust versus Yeah, I know. But even though these are pretty wimpy, they're very fuel efficient. These could be run for hours, days, weeks, months, years before they run out of fuel. What difference would that make going to Mars? If they upscale this technology and use it on a Mars ship, the trip to Mars might take 40 days. 40 days versus 300? Okay, I vote for 40 days, okay? Makes a lot more sense. By the way, if you want to learn more about this type of rocket engine, adults or get your parents or your teacher's permission, look up the Dawn space mission, DAWN. It's a NASA space mission that's already flown this type of rocket engine in outer space. It's fascinating. Okay. Now, I mentioned earlier that electrons were very strong for their size. So let me put these up here. Electrons move very easily over things like metals. Metals are called a conductor. So if I turn this on, this whole thing will be covered in, because this metal ball will be covered in electrons. And these metal pie pans will also be covered in electrons. Remember what I told you earlier about if you put electrons next to electrons, what happens? They push apart. Let's see what happens to these pie pans. Here we go. Well, it makes an instant mess. And hopefully didn't knock out my camera too bad or my microphone. All right, so I think we're about running to the end of the demo part of the show. I do want to leave you with one thing that's very important. Okay, so we've had some fun with physics today. We learned what it is, and you can start looking for where it shows up in your life, because I promise you it's everywhere. Okay? Look, some of you may go on to become rocket scientists someday. I'd be really okay with that. But even if you don't, learn how your world works. It will give you real power in the real world. I mean, do you like sports? I guarantee you, people in the Olympics who win medals use physics. They have studied and used their physics lessons. They know physics and they use it. Gives them an advantage. But it doesn't have to be anything like that. Do you like cooking? There's tons of physics in cooking. Do you like music? There's tons of physics in music. Do you like dancing? I've done shows on the physics of breakdancing. There's tons of physics everywhere in your lives. Learn how your world works and use that knowledge. Use it for whatever you like to do. Because I promise you, if you're doing better at something you already like to do, doesn't that mean you're having more fun? And that's what I want you to have. I want you to have real power in the real world, and I want you to have fun doing it. Okay? So, on that note, I said if you have any questions, type them into the chat. Can you read me any of the questions now?
Yeah, at this point, we don't have any questions in the chat, but I'll keep my eye out. Maybe somebody is out there typing right now.
All right. If you do have any questions, make sure to type in the chat right away. And oof. By the way, we never get to all my demonstrations. I never have enough time for everything. So while we're waiting, maybe I can show you some other things. Oh, I didn't get to my air cannon here. This is kind of fun. Oops, wrong button. Let's try this one. Here we go. So don't worry. The only thing that this shoots is little foam emoji balls, kind of like this one. It's already got one loaded in there. This is a demonstration of how you can turn energy from one form into another. So what I'm doing right now is I've got a little electric pump here. So I'm using electrical energy. It's turning that electrical energy and it's squeezing on air, which takes work to do. So it's actually squeezing air and cramming it into this little container. So we're creating potential energy. We're storing up energy in this bottle. And when I pull this trigger down here, all that potential energy that's stored up gradually is going to be released all at once, and it'll work on the ball that's inside this tube, and we'll get it moving really fast. So it's going to go from potential energy to kinetic energy like that. How are we doing here? We've got to get a little bit more pressure in here. And I think we're about ready to try this. Okay, in 5, 4, 3, 2, 1. Whew. Wait a minute. I think I can find, let me see if I can find the ball that came out of that. Yeah, here it is. Hey, check this out. I promise you, if I shot you out of a cannon, you'd look like that too. This poor guy, he's been shot out of a cannon so many times. I feel so bad for him. No, not really. Anyway, any questions at all?
No questions, but we did get a shout out from Rajendra, who is watching from India at
Oh, that's so
4:50
cool.
a.m. in the morning. So
Hi,
thanks for joining
Raj.
us.
Thanks for getting up early for us. Another demonstration that I have that's really fun is this one down here. This is a hovercraft. I'm going to use my trusty leaf blower again. This is actually a demonstration I used to do a lot with when I'd have doing live shows with kids. Because what I would do is I'd actually have a kid ride on this. Let me cinch that up. There we go. So right now, remember I told you about friction earlier? Right now there's a lot of friction between the bottom of this board and the floor. Now, for friction to work, things have to be touching, right? So there's a lot of ways I could reduce friction between the bottom of this board and the floor. Me, I like getting rid of friction altogether. So with a hovercraft, you do that by shooting air under the board. So when I turn this leaf blower on, it'll put air under the board, and that air pressure under there will lift the board up a tiny bit, but enough that the board and the floor aren't touching, and all that nasty friction just goes away. So instead of putting a kid on here to do this with, my wife donated this lovely basket of stuffed animals. So, but you'll get the idea. Whoops. Or, give me a second. My leaf blower came loose. Let's try that one more time. There we go. See how easy that is? With one little leaf blower like this on a board this size, it can almost lift me up, and I'm a pretty big guy. With a board that was about 4 feet in diameter, was what I used to use, could lift over 400 pounds with just the force of air from one little leaf blower. So look up hovercrafts. So they actually use hovercrafts in the real world to move all kinds of things around, people and equipment, all kinds of stuff. They are amazing things. And then the coolest thing is there are versions of hovercrafts that can go over pretty much any kind of thing. So you can go from land to water to snow. It doesn't matter. They don't care what they're gliding over. They'll just glide over pretty much anything as long as it's not too rough.
We have a question in the chat, Mike.
Yes, please.
The question is, what type of matter would Plato be?
Plato. Oh my goodness. Well, let's think about that. Maybe we could do it by process of elimination. So is Plato a gas that you could breathe? No, I don't think you can breathe Plato. Is it a liquid? Could you pour it? Maybe. But it'd be like a really, really, really thick liquid. So maybe not. Is it a solid? Well, it's probably somewhere between a solid and a liquid, would be my guess. Just something that's very, very, very thick. But that's a great question. Um, I'll have to look that one up. By the way, here's something you should know. I don't have all the answers. I can use my science background to maybe come up with some good guesses, but and it's okay. And if you don't ever be afraid of not knowing the answers and admit to that. There's nothing wrong with not knowing the answers. Just don't stop with that. Just don't go like, I don't know. Then go find out. That's the real adventure of science. It's like if you don't know the answer to something, go find out. You might discover something that no one has ever thought of before. And that can be really cool and exciting and fun. All right. Do you have any other questions? We got a few minutes left.
No other questions in the chat right now.
Okay. Well, let me think. What else have I got to show you guys? Oh, you know what? I'm going to actually talk a little bit about the plasma ball. I never get to talk enough about this. I actually have done entire shows on the plasma ball alone. So let me zoom back in on that. There we go. Let me put this back over. It makes it a little easier to see. So this ball is full of plasma. Now, I mentioned earlier that it takes a lot of energy. You have to dump a lot of energy into something to make it into a plasma. So if there's a lot of energy in that stream of plasma, and my hand's sitting right smack on top of the ball, why am I not screaming in pain? Because clearly that plasma's got to be hot, right? Let me zoom out a little bit here so you can see it a little better. See how it's hitting there? My hand's getting a little warm, but it's not burning me. Well, there's a couple reasons. One, this is a glass ball. Glass does not conduct heat energy very well. It's called an insulator, but it's very thin glass, so that's not the whole story. Do you think there's very much plasma in that ball? No, it's very, very skinny little streamers. The streamers themselves are hot, but there's so very little plasma in there that overall there's just not a lot of heat energy that can come through the glass that could hurt me. So that's a good thing because these are really fun to play with. And that electricity likes to come to where my hand is. That's a little bit bigger topic, but when I'm actually touching it, I actually become part of an electric circuit. So the electricity actually is attracted the easier path for the electricity to go to is over to my hand. I don't know. It just looks really cool. And there's a lot to learn about this, so I do encourage you to learn more about this. Like I said, I do entire shows on plasma balls alone.
We
Well,
have another question.
good.
What is the difference or similarity between theories or hypotheses?
It's the same thing. Like maybe a theory like Einstein's theories of relativity, they might have a little bit more proof behind them, but it's still a theory. A theory or a hypothesis is really the same thing. It's easier to say theory than hypothesis, but that's about it. It's a good question though, because I think people can be confused by that. Well, we're just about out of time, so one time for one more question if anybody has any more questions. And there's always more questions, and there's always more things that we could do. So keep exploring, keep learning about your lives. If you're interested in my shows, please look me up on look for the physics experience online. For those of you in India, talk to my friend Raj over at Business Value India. Um, uh, and have fun with your lives. Really have fun, okay? Thank you. And there's so much more. The Science Expedition Science Festival is just getting started. So please go to science.wisc.edu. Learn about all the other things happening. I'm actually performing in some more physics shows over the weekend live in person, although there will be some live streaming events on Sunday. So look that up. Look up the wonders of physics. Go to science.wisc.edu to learn more about that, or go to the wonders.physics.wisc.edu and it'll give you the links for the shows on Sunday.